fuel. This the longest, this not so long, right? It's not going to take as long to do that. Okay, so far, hydrogen fusion stops, it collapses the helium core, becomes a red giant, right? Okay, it does helium fusion along there, and then the carbon core collapses here, right? Right there. That's the collapse. This is the collapse of the helium core. Is this thing here, right? Okay. And then we have carbon fusion. If we've got enough mass, I don't think our sun is going to pull this off because we start off with 1 times the mass of the sun, and if we lose 7/8 or 3/4 of our mass when we become a red giant, we're going to be like 1/4 of the mass of the sun, 1/8 of the mass of the sun. So we're not going to. Isn't that sad? No happy retirement home for our sun. Okay, and these things are white dwarfs. Dwarf. Right? And then eventually it becomes degenerate matter. What's degenerate matter? It's matter that... What? That's right, yeah. It's, we can have all sorts of fun. Basically, it's, you know how an atom is... It's not neutron star material. You know how an atom has got like mostly nothing? If you make an atom the size of the rose garden arena, the nucleus is like a golf ball in the middle. Yes? Okay. This not so much. This is just nuclei and electrons, cheek and jowl, all mixed up, right? Okay. A neutron star is so much gravity that the electrons have been stabbed into the neutrons or into the protons, and it's all neutrons. Everything is a neutron. So this is not neutron star material, but it's still very, very dense, right? Okay.
So this collapse is very, very gradual. It's not like
it's
not like a billion years and then.
Yeah, I don't know what the time scale is, but it can be a white dwarf for quite a long time because you can see a lot of white dwarfs out there, and they're very, very hot. But since they're so small, they're not very bright, right? Okay, how do we know all this? It's like, well, there we go, right? Here's a globular cluster. All these stars are about the same age because we think it's just a bunch of matter that got. And this is not like a galaxy. This is much, much smaller than that. And it's a chunk of material that just got abandoned in space and collapsed. Just like when you breathe on a warm or a cold day, your breath condenses instantly, right? So these guys all condensed instantly, and they all have about the same age. And so if we make a map of them, it's like, do you see any similarities here? So here is this main sequence of a globular cluster. What has happened to all the big stars? Where have all the big stars gone? Long time passing. Yeah, they're all dead, right? Okay, they all died because they're just that they don't live very long, right? Okay, so these guys are all gone except for who knows what these are, right? They might be ones that got born later, right? They weren't all at the same time, just okay. And so if you look at this, these guys are on their way to becoming red giants. Why are there so few out here? They don't stay there very long, and so it's like a race where people all are running slowly, but suddenly they speed up and they're going to be more spread out, right? Why is there a gap here? Well, that's because that's actually a place where the star's radiation is I think its light is unstable, so it's a variable star, so it's hard to pin them down to one brightness, okay? And then here it is, and then we just don't see their white dwarfs. Maybe these runners haven't gotten there that far, okay? The really fast runners haven't gotten to white dwarf yet. Right, that's kind of cool, isn't it? Notice the axis here is color, blue, red. Right? They're talking about the spectrum here. Blue stars are hot, red stars are cool, bright, dim. Sorry. All right. So now we get to the fun stuff, right? Planetary nebulas, the nebulas that are not unlike any other nebula, right? If you've got a mass, if it's a white dwarf and it's a mass between 1 and 7 times the mass of the sun, okay, these guys shrink, they start to spin really fast. And when they spin fast, the magnetic field tends to make these little polar jets that shoot off, right? And what you've got is, it's kind of fun. You've got the white dwarf spinning. It's shooting material this way, little polar jets this way. And there's also stuff around here, right, that's been shot off of the star as it went through all of its paroxysms of demise, right? It's red when it became a red giant. When the helium core collapsed and it became a white dwarf, it's shooting stuff off into space. This stuff's racing away from the star. relatively slowly, right? Okay, now, the other crazy thing is that these things are binary stars. A lot of stars are binary stars, right? So maybe this guy's orbiting another star. So here are these guys spinning around each other, yeah? Okay, now, what you need to know is that white dwarfs have an atmosphere, kind of a blousy atmosphere of stuff around them that didn't collapse onto the star, right? Now, as these guys spin, some of their orbits might carry them close to each other. They might have an orbit like this, where they're like, right? Sometimes they're far away, sometimes they're close together. They're like close, far, close, far. Every time they come close to each other, one of the stars might encounter the atmosphere of the other star, right? They come so close that they actually are throwing chunks of each other onto the other star, right? Usually one of them is shooting stuff into the direction like this, and so it's like, do you guys have a vertical agitator washing machine? Have you ever thrown a blanket into one of those things and tried to spin it? And all the stuff is on one side. What does it do? Does your washing machine get up and start to try to walk around the garage? Yeah, it's just crazy. You stick one towel in there, right? And it all is on one side, and the machine is trying to spin, so it's going right, going crazy. Yes, no, we've never done this. Okay, you'll do it in college. That's something you can learn in college, right? Okay, so if you've got something spinning and you throw something onto it, it's going to go crazy. It's going to be like whoa and spin in crazy directions. These polar jets are going to erupt material. They're going to go poof and shoot material off into space. This is what they think makes these planetary nebulas, is that these guys encounter each other in unpredictable ways. They're throwing chunks of material onto each other, and it's making these jets. Now this one is doing a stately thing. It's just sort of, it's not doing anything chaotic. It's drawing a nice, fairly symmetrical hourglass shape. This is the classic planetary nebula shape, is that we're shooting stuff like this. We're orbiting a partner in a serene way. It's kind of like we're holding hands, and we're spinning at a constant speed like this, right? Okay, so this is a very unchaotic thing, and our jets are just shooting off in this direction, and as we draw it, we draw these little hourglasses like that, yeah? Okay, so, and we're seeing this guy down into the hourglass, so we're looking at this thing like this, yeah? And then you can see in the center, there's the star right there. It's clearing out its little path. That's kind of pretty. Isn't that pretty? Yeah. It looks like an eyeball, doesn't it? Shannon doesn't like this picture. She's like, get that eyeball off the desktop of the computer. No. It's a pretty eyeball. How about this guy? This is called the Eskimo Nebula, not because it looks like an Eskimo, but because it was discovered by an Inuit citizen. No, just because it looks like an Eskimo. What is this stuff here? Is that possibly the Oort cloud that was surrounding this star system? Like icy gases, icy chunks of stuff orbiting it, right? Notice that they all look like they're getting pushed off into space by radiation pressure, right? That's like the explosion in the radiation of the star. This thing has not so much, it's not evident the point symmetry of it, right? These things have something called point symmetry, where a point here is symmetrical with a point there. Hard to see with this one. Easy to see though. This is an hourglass shape, right? This one's obviously point symmetric. Look at this chunk here. That was like a moment of indigestion from both ends of the star. Like, whoa, what was that, right? Sorry, bless you, right? There's a chunk of stuff just going, and they were released at this stuff is all moving away from the star, and these were released at pretty much the same time, right, from both ends of the star. Okay, here, this is classic point symmetry. Okay, point symmetry just means that something here, if you go straight across the star, there's something there. It's three-dimensional, so two-dimensional pictures don't always show it perfectly, right? This stuff here corresponds to this stuff here, this stuff, that stuff, this not. Well, maybe it's up behind that. Who knows, right? Okay. Classic point symmetry. Look at this. Burp, anti-burp. Burp, anti-burp. Burp, anti-burp, yeah? Straight across the star, there's stuff, because it's shooting stuff in both directions, yeah. It's approximately the same. It's not exactly, right? Because it's just a chaotic event, right? So it's not exactly, but it's pretty close, right? Right? Okay, now, if we now have 1.4 times the current mass of the sun, if we're less than that, pretty much our story ends here. It's just going to become a white dwarf about the size of Earth. And there's something called the Pauli exclusion principle, which keeps electrons from occupying the same quantum state. And since degenerate matter is electrons and nuclei just sort of cheek and jowl. It's pretty dense stuff, but it's not neutron star stuff.